Hello and welcome to the second video in our series about Black Death, 3-pound plastic combat robot. This video is going to be about the manufacturing of the robot. If you're interested to know how we decided on this design, you can check out the last video. It's a very interesting delve into the robot that preceded this one and the different improvements I tried to make as I designed this robot. As we get into these videos that are really about the build, we're going to focus, instead of chronologically, we're going to focus on one subsystem at a time. And in this video, we'll focus on the drive system. And to kind of ground everything, the format I'm going to go with is at first we'll zoom in on the completed robot. I'll take apart the system that we're going to go over in the video. We can look at all the components, and then we'll go through the video of it actually being created. So let's dive right in. And the first thing I'd like to point out is just how close some of the tolerances are here. This was maybe, a poor choice in design. But you can see that there are some components, a white switch here, a red piece of nut strip here, which each have screws, 1, 2, 3, 4 screws that hold them in place, and that actually is very close to interfering with the tread of the wheel. I in fact had to buy special low profile fasteners, and even then there are just a few tens of thousandths of an inch between the heads of those screws and the wheel itself. And that made this entire assembly here very difficult to create. There was lots of fiddling and trying to just shave off a fraction of an inch here and there. And as we take it apart, we can see what all the components are that went into it. So we can take off the sidewall and the weapon. What we have here is a Fingertech Gold Spark 50-to-1 gear motor. This is what I chose to go with for the project, and it might not have been the best choice, but we'll get into that later into the post-mortem videos. For now, we can see how it was mounted in the robot, fully enclosed, one on each side, so the other motor would be mounted like this, and it was fastened by 2 screws that went into the gearbox, and onto the shaft was affixed a 9-tooth pulley via 2 set screws that drove a belt to another 9-tooth pulley, so effectively no gear ratio there. Okay, let's take a little bit of a closer look at the wheel assembly, because this was one of the places where I wasted the most time. This was in that area that I showed earlier where the dimensions were super tight. So there's an external retaining clip to keep this hub from popping out. Once it's removed, that can just be pushed through. And you can see that this is made of 2 components. The silver one is the hex hub that comes with Banebot's wheels, and the red one is a modified Fingertech pulley. And you can see that I removed some material because both of these have a feature to allow for set screws. So I only need one of those once they're epoxied together, and I needed every little bit that I could get. In fact, it got to the point that I was using this. This is actually a piece of business card that was laser cut, and this moves the wheel, just a few thousandths of an inch, and that was absolutely necessary. There are also some shims on the back side. These ones are from a 3D printed material. It was so bad that even with all those shims, I had to remove some raised lettering from the side of the wheels. So definitely, this is the kind of thing that if I had given myself 2-3 more millimeters of space, I could have saved easily 8 hours, 10 hours of fiddling with these components, and a lot of stress about, if I ruin one of these and I only have one extra, I could put myself in a position where I just can't finish the robot. And that's about it for the mechanical drive system. Let's go to the video of it being manufactured. Just cutting the motors down to length, and then realizing that holding the motor in the vise, maybe cut at an angle, it's kind of messy, so it was actually easier to hold the Dremel in the vise. I also tried to make the drive shafts for the wheels on a lathe with this arrangement here that you can see, but the part is sticking out way too much and it's way too thin, so the surface finish was terrible. It wasn't actually the right size in the end, but interesting at least to get some time in on the lathe. I ended up buying a piece of stock that you see here and just cutting it the size that was already 3 millimeters in diameter. All the Dremel cuts are a little rough, so we just deburr them and smooth them out so that you can do the press fit pulleys over them nice and easy. This wheel here is just abrasive. It's actually kind of rubbery and soft. You can stick your fingernail into it when it's not spinning. There's some cool standing wave patterns as the machine spun at different rates. As it slowed down, the waves changed. What you see here is a time lapse of a fixture that's being printed. So this fixture is meant to hold in the pulleys, and it's important to make this fixture because the pulleys have 9 teeth. So there's no real good place to clamp them, and being made out of aluminum, it's really easy to over tighten and break these very small, delicate teeth. So this will allow me to hold it in place and mill. So here I'm just skipping between the different passes that I made on this part, and the first few go pretty well, but it becomes apparent after the first couple that this is actually made out of 2 pieces. You can already see it here. There's the outer piece that's been pressed onto an inner shaft, so these 2 cylindrical pieces pressed into each other. And as we get deeper, we'll actually get into the threads where the set screw go, and right there you can see that they're lined up. But after I take this pass, something happens, they shift, and they're no longer aligned. And in this piece, nothing too terribly bad happened. But this actually was a big pain. I ruined 2 other pulleys trying to machine them in the same way because when those 2 cylindrical pieces slipped and misaligned in the other pieces, they just totally ripped apart. So eventually I moved on. Instead of milling, I tried to just grind away the excess material. This took longer and the parts got pretty hot, but it was much more controlled. Then I tried to epoxy together the hex hub and the pulley, but you can see in this one it was messed up immediately into a cup of acetone, and just to remove all the epoxy and try again. It's hard to get the 2 pieces to stick together that I want to, the pulley and the hub, without also getting the shaft epoxied in. And I wanted the shaft to still be removable. I could just take out the set screws and replace it. So here is another attempt. So I epoxied this part together and I let it sit to dry and cure. And I removed the pin that was holding it in alignment because I didn't want that to get epoxy to the rest, and I thought it would be fine because when I left it, it was perfectly aligned. But now you can see that it's way, way off. So I have to remove this epoxy, and I'm going to try to do that with a torch by overheating it. I think this theoretically would have worked, but I just went way, way, way too long. I actually stopped when I saw that the part was starting to glow from its own heat. Wow, it melted. Well, I screwed that up. One last try with the epoxy. This time it worked. So I was having a lot of trouble getting my wheel assembly to work because there were just too many close tolerances and things were rubbing. And part of the problem was that these wheels actually have some writing on them which sticks up proud, and it doesn't really serve any purpose, of course, so I'm just highlighting it with a Sharpie so that you can see it. And I found that this wheel is actually very tough. If you try to cut these letters off with an X-Acto knife, it really doesn't leave much of a mark. But if you heat up the knife, thank you so much for watching this video. If you enjoyed it, please like or subscribe, and I hope to see you next time when we talk about the chassis.